Good morning. Hopefully I can continue the wonderful streak of lectures we've had so far. And I'm going to break the pattern and take you away from the Midwest. We're going out to the West. So I think I'll start things off just by giving you some context and a little visual tour of my watershed while I talk. Because it's a little different than what we've seen today. So the Wallsburg watershed is 70 square miles of beautiful intermountain landscape located in north central Utah. It's part of the Provo River Basin that you can see to the north here. And the Wallsburg watershed has been targeted as a significant source of total and dissolved phosphorus for a nearby reservoir because of the disproportionately high loads of P and a small amount of discharge water. So this outlines the watershed here. It's not very big. These are the tributaries that we focused on. They're the major tributaries that have water in them year-round. In orange, there is Little Hobble Creek. In blue, running the length of the watershed, is the aptly named Main Creek. And then at the other end, in green, you can't really see it, is Spring Creek. And we'll talk about those, especially Main Creek and Spring Creek. The dots on the graph represent all the points we ended up sampling. Anyways, although phosphorus concentration at the outflow of the watershed has been monitored since the late 1980s, little work has been done to actually find the phosphorus sources within the watershed. And it's simply been assumed that agricultural practices are most likely responsible for the high phosphorus loads. But this is a mixed-use watershed, dominated by shrubland and woodlands, with less than 8% of the land use in low-intensity, small-scale agriculture. Alfalfa fields, hay fields, some cattle, some sheep, but not much. So is this a good assumption? So we're going to take a look at some sites. Like here you see the source of Spring Creek, which is a spring, and there's some interesting results there. We could ask ourselves, is there some kind of subsurface pathway, with the groundwater in situations like that? Is it coming simply from stream bank erosion like we've talked about today? Here you can see my slightly outdated shapefile from a whole year ago is now incorrect because of some stream bank restoration projects, restoring meanders. So maybe there's a sediment load there. Could it be coming through different snowmelt pathways? Because snowmelt is the dominant form of precipitation in this watershed. There's very little precipitation at any other time of the year except for in winter. And this is all important, of course, because downstream the water flows out into a reservoir, which supplies municipal water for Salt Lake City. So I guess our first question that we wanted to answer was, well, what does the soil phosphorus levels look like? Just at a basic level. How does that correlate across the watershed? So you would expect to see higher levels of P in the agricultural fields compared to the shrublands and woodlands. After doing Olsen extractable, though, these were our results. We asked this question, and the answer is no. There's no significant difference between the agricultural soils and the shrublands and woodlands. In fact, the shrublands and woodlands are perhaps even slightly higher than agricultural soils on average. So that's interesting. So maybe we should turn to the water to get a better snapshot. We performed synoptic sampling, which simply means to hit as many sites as you possibly can in as short a time as you possibly can. So we went to 19 sites in less than 2 hours, where we collected water samples and flow measurements so that we could calculate some kind of phosphorus load. Can I just say, it would be nice if the Hawk flow meter was a little bit more water resistant and waterproof. Learned that the hard way. But here are some students taking flow measurements in a stream. All right. The water samples were brought back to the lab, where we did some general fractionation into reactive portions and total portions. So let's take a look first at some of the results for Main Creek. My graphs are going to be like those we've seen today, based on distance from the top, before any interaction with agricultural land, all the way through the landscape there, to see what it looks like. To give you a sense of the flow we saw at different times of year, let's take a look at this. You can see the different months denoted by the different lines. We have flow rate in cubic feet per second and distance in miles on the bottom. The little markers along the x-axis represent the confluences with Little Hobble Creek and Spring Creek, so you would probably expect an increase in flow in these areas. Lo and behold, in May, that's when we saw the highest discharge in the headwaters. Again, snowmelt is the dominant form of precipitation here, or of water supply. And but then it drops off pretty rapidly. Most of the water is diverted into agricultural fields. Some of it's even diverted across the valley and doesn't directly return in a quick and short time scale. So here's what we see in terms of total phosphorus and total dissolved phosphorus concentrations along Main Creek. Total phosphorus is the chart on the top, and total dissolved is on the bottom. The red line is new to these graphs, and that is a concentration related to the TMDL that the state has set for these waters. In terms of total phosphorus, pretty much everywhere along the reach of Main Creek, it exceeds the TMDL. And except for maybe in March and May or July there, where the flows are initially low. But we do see a general increase as we move downstream through the agricultural lands, especially in total phosphorus. So maybe there is something to the hypothesis that the agricultural land is supplying some source of phosphorus here. There's especially some increases in total phosphorus after the confluence with Spring Creek. But to get a better picture, because sometimes there was no water in the creeks, and obviously you can't measure water if there isn't any. So to get a better picture, you have to look at loads, which is a simple product of the concentration and the flow rate. And here it becomes even perhaps more clear that when Spring Creek and Main Creek merge, there's an increase. Especially it's pronounced in March, but even there's slight increases later on in the summer when there's less water. By the way, I don't have November's data for total phosphorus. It's still in the lab. So maybe we should take a closer look at Spring Creek. And Spring Creek is really interesting because of its headwaters. It's a spring, but it's beautiful at certain times of the year, and then completely covered in algae at other times of the year. And which is interesting because it's you would think that spring water would be this pristine source of groundwater. Well, the flow rates, as we would expect at the spring, are fairly constant at any time of the year. Again, in the summertime, the water's diverted, at least initially, and then you get return flows. But here, it's, total phosphorus and total dissolved phosphorus, they exceed the state TMDL, even from the spring. So, and by the way, these scales are similar to Main Creek in terms of concentration. Perhaps we can get a better look if we look at load again. And we see that total dissolved phosphorus stays fairly constant throughout the reach of Spring Creek, although it is lower, obviously, in the summertime due to lower flows. Whereas total phosphorus, which is often associated with sediment, is much higher compared to dissolved. So, it's interesting that it's high from the very beginning. We also see it increasing at certain places along the stream. So, perhaps there are some land management practices that need to change. But maybe there's also this background level. Could it be helped? Maybe it's from faulty septic systems in town, but maybe it should also just be accounted for if you can't do much about it. This is an example of another way to look at the data. We take just one time of year and look at it in terms of phosphorus fractions. And here it's, again, pretty clear that at the beginning of, at the spring, as you would expect, most of it is in a dissolved form. But as you go down the watershed, it diverges, and there's definitely an increase in load due to sediment associated total phosphorus. So I guess this is a specific site, but some takeaways would be that soil testing is really important. Obviously, if you're going to be doing water quality studies, by hitting multiple sites at a given time, it's easier to identify background levels of phosphorus and track how that changes down the watershed. And doing some level of p-fractionation can better clarify whether or not it's a sediment source or not. So there's obviously a lot of work to be done. This is still in its childhood, so to speak. Onto the GIS analyses, onto sediment studies in the streams. This is a good start, I think. Any questions?
Questions, so we can open up the floor for that.
Yes.
The base of the TMDL was higher, or the natural background appeared to be higher than the standard that was set. That seems to be illogical. Isn't there some type of requirement that the standard has to account for the natural background?
So yes, as best as I can tell, the TMDLs were back calculated. There were load estimates for the watershed based on certain flow rates, and then they came up with a number for the concentration that you would expect to see in the water at those flow rates. And so, it's a bit perplexing and seems illogical that the background level would be higher than the TMDL. But that is what it is, and that's why this watershed's kind of interesting to work with. Because on the one hand, there are some reaches that could be improved in terms of sediment and erosion. But what can you do at a spring source like this? Even the NRCS at one point said that Spring Creek should be studied a little bit closer, and we should figure this out. And nothing's been done 6 years since that was said. So maybe some reassessing and some modifications should be made. That's as best as I can answer you.